Okie dokie. So, guys, we are at a slight disadvantage right now simply because what we are about to talk about is best understood having just messed around with the food coloring water. So, imagine now the last 47 hours didn't just happen. And hey guys, look, equilibrium, blue water, 70-30. Wasn't that neat? Now let's keep going. So, what we can do now is we can talk about the interesting things that happen at equilibrium. And guys, we alluded to this last year. I actually taught you this last year, but chances are good you guys understood because you guys are bright. But chances are good you're the only people in the room that did understand. So, guys, this is important fundamentally to understand about equilibrium, because equilibrium's root word, of course, is equal. So we need to talk about what is actually equal at equilibrium. And so, guys, in order to talk about this, we need to, I use the word distinguish. I would say a better word would be differentiate, if you know what that, to separate, to figure out what's going on. So guys, when we talk about equilibrium, we need to know what is going on with rate and what is going on with concentration at equilibrium. And again, we did learn this last year, but I believe it's worth talking about. So guys, the idea is this. And just let this soak in for a second. So guys, these are actually graphical representations of a generic system reaching equilibrium. Well, and maybe we could back up and talk about it. Which one is the reactant, A or B? How do you know it's A? Because you start with some, right? A is going down, which means you started with A, which we conveniently call the reactant. And then you'll notice we started with no B, and so that we would then understand to be our product. And so this system is simply going from A to B. So, guys, what do these two graphs have in common? They end up with straight lines. But even before you start looking at the data that's plotted, what do the graphs have fundamentally in common? Time is on the x-axis. Okay, so what we are doing is we were looking at a chemical reaction taking place over time. In the first set of data, you'll notice that we're tracking concentration. This is basically the mason jar thing all over again, right? Where the concentration of the reactants go down, the products go up, da-da-da-da-da-da. Only now this reaction doesn't go to completion like the mason jar thing did. It reaches equilibrium. And then, guys, on the right-hand side, you'll notice that we're tracking rate. So, guys, given these two representations of equilibrium, we can now talk about what is happening to rate and concentration at equilibrium. So guys, let's do rate first. You'll notice that as a reaction starts, so this is the rate that the reactant is going away, right? So initially, the rate that the reactant is being consumed is very high, and you guys already understand this, right? Why does this have a decreasing slope? What does that indicate? Decreasing, not concentration, decreasing rate. Guys, pause there. Make sure you're clear on that. So guys, what we see here is the rate. This isn't, I can't write, but this isn't linear. The speed of the reaction is not consistent. The reaction is slowing down as represented by the decreasing rate. So guys, why is the reaction slowing down? Decreasing concentration, which fundamentally means what at a molecular level? Fewer collisions. So guys, the reaction here is slowing down. What is happening to the rate at which the products are being produced? It's also slowing down. Do you see that? This has also got a decreasing slope. One is a positive slope because it's being produced. One is a negative slope because it's being consumed. But in both cases, the slope is decreasing. They're both becoming flat. So the speed at which the reactant is consumed is slowing down. The speed at which the product is being created is slowing down. But that's all stuff we already knew, right? So now what's the big idea? Well, guys, what little magic thing happened there? eventually the rates become equal. And doesn't that make sense? That if this is slowing down and if this is speeding up, eventually they're going to come to the same rate. But notice they stay at the same rate. And that was the whole idea with this thing, right? Eventually the amount of water transferring forward and backward cancel each other out. The rates are the same. That's equal. Go to the left. Guys, this is the 70-30 thing. Only it's technically backwards. This would be more like 30-70. But let's talk about what's going on. Now we're following concentration. We understand that we start with a lot of reactant and no product. The concentration of the reactants go down, the concentration of the products go up. When this reaches equilibrium, what happens to the concentrations? They stop changing. What's the word we use for that? They don't become the same, they become constant. And guys, that's the overriding principle. At equilibrium, two things happen. At equilibrium, the rates become equal. At equilibrium, the concentrations become constant. And can you picture that relative to our flippy thing? So guys, thinking about our water flippy thing, what about our water flippy thing represented the fact that the concentrations become constant? Right, but that was so, yeah, and so the 70-30, right? That eventually we did this and the amount of water in the tubes stayed at 70-30. The concentrations become constant. Notice that doesn't mean equal, it just means constant, 70-30. So guys, what in our water flippy thing represented the fact that the rates are equal? In the tubes, not the cylinder, the tubes. So when we were doing this, we saw that the rates became equal because the amount of water in the tubes became the same. So guys, the summary then is at equilibrium, the rates become equal and constant, right? They have to be constant to be equal. So the rates become equal and the concentrations become constant. You guys good on that idea? Okay. So now what we're going to do is we're going to talk about the thing that Catherine got us thinking about a little bit. And that's this idea, well, let me not tee it up that way, but you'll see the connection in a minute. So guys, there's another important thing that you need to understand fundamentally about equilibrium. And it's this. Equilibrium can be reached from lots of different directions. Now guys, in order to explain this to you, this provides a good opportunity for me to introduce you to the one named reaction that you need to know in AP Chemistry. Guys, if you don't understand that, in addition to all of the other things that makes organic chemistry really evil, there's another thing that makes organic chemistry really evil. Most of the reactions that you learn about when you go through this have names. The Friedel-Crafts reaction, they're named after the people that discovered them and many times patented them. And so guys, you not only have to know the chemistry behind it, you also got to know the name of the dead guy that figured it out the first time. It's horrible. So, guys, there's one named reaction that you need to know in AP Chemistry. This is what is called the Haber process, H-A-B-E-R. This is called the Haber process, and it looks like this. Write it down. This you've got to know for the test. On the AP test, they will have no qualms about saying, what effect does a pressure change have on the Haber process? I don't know why they picked this one, but it's the one they picked. Interestingly, guys, if you're a World War II buff like Ashley's dad, look up Haber process. Some people would say that this reaction actually helped us win the war. The problem is that we had so many of our young men over in the Pacific and European theaters during World War II that we ran out of farmers, and there was a food shortage. And that's exactly what it is. What Haber figured out how to do was to take elemental hydrogen and nitrogen. It's diatomic, but it's still elemental. Figured out how to take diatomic hydrogen and nitrogen and get it to form ammonia, which is NH3, which is fertilizer. If you've ever driven through well, North Dakota. It's just one big farm. And everywhere you turn, there are these huge tanks that say danger NH3 on the side. They dissolve it in water. But guys, literally, when they industrially fertilize, they don't go down and buy a big bag of Scott's Turf Builder. They are literally spraying nitrogen, NH3, ammonia, on the ground. It's the most efficient way to fertilize, and Haber figured out how to get this reaction to make lots of ammonia. Guys, it turns out, and I hate this, this is actually a misprint. This should go in both directions. This is an equilibrium process. What Haber did is he figured out how to tweak this reaction relative to pressure and temperature to increase the yields to the point where we would get out a lot of NH3. So, and I think you guys probably, I don't know what you wrote down, but my hope is you wrote this. Because guys, that is the balanced Haber process. So now you know about the Haber process. So guys, with all of that said, here's some data. And guys, please notice that this is concentration data and this is not rate data. Let me give you a second to process. The problem is that I don't even know if I can say this out loud in a way that makes sense to you. Let me try it. So this reaction does not favor products. If you take nitrogen and hydrogen and put them together, they will make a little bit of ammonia, not much. Maybe I could say this. The Kc for this reaction would be Is that okay? Okay, so that's the Kc for this reaction. The Kc value for this reaction is way below 1. Exactly, right. How? By the things that affect K, right? Little k. Change the temperature, add catalysts, actually change the pressure as well. And we'll talk all about that when we do Le Chatelier's principle. But he was able to figure out a way on an industrial scale to tweak this reaction so that we could change the equilibrium so it would favor products. Yeah, I think there's even a little aside on this in your book. If you're, do you know where it is? Oh, really? Oh, there. Oh, yeah, there it is, guys. So if you look on page 615, I can almost guarantee you that was shot in North Dakota. Seriously, that's what North Dakota looks like. That guy looks like a North Dakotan. And this is all about the Haber process and how they were able to do what they did. Are you just rubbing?
Yeah.
Oh, okay. Yeah. Yeah, so one causes the other. That's an interesting question. So I like your word mirror, right? There's a reflection, and in a matter of fact, the ratios are equal. We established that last time, that your K forward divided by K reverse ratio is equal to your product divided by reactant ratio. Why is that the case? It's not coincidence. The reason that that's the case is because your K forward, K reverse ratio determines what your concentration ratio will be. In the same way, what was it that determined that this settled out at 70-30? The size of the tubes, right? And so the idea is that those K values, again, as represented by the tubes, determine your concentration ratios at equilibrium. So it's not coincidence that they mirror each other. One causes the other. Is that okay? Yeah, so guys, hold on. I want to come back to what we were talking about because this is the important point. So what I've got here is data representing two different runs of the Haber process. Notice that we're tracking concentration in both examples, and notice that they're both versus time. You'll notice that they both reach equilibrium. How do we know they both reach equilibrium? Concentrations go horizontal, right? Which means they are what? Constant. Good. Now, guys, how is trial A different than trial B? Right. Here, guys, we are starting with a lot of H2, some N2, and 0 NH3. Over here, we're starting with 0 N2, 0 H2, and all NH3. You'll notice, guys, that they come to exactly the same equilibrium. So, relative to our flippy tubes, right? What are we talking about? Well, the analogy is this. When we did the flippy tubes, we started with all of the water in the reactant tube and none of the water in the product tube, right? What if we had started with all of the water in the product tube and none of the water in the reactant tube? You'd end up at the same place. Does that make sense? So guys, it does not matter where you start. A chemical reaction will always fall to the same equilibrium. It does not matter where you start. Yeah. It doesn't matter. And that's the point behind question number 5 out of the homework. It does not matter. It has nothing to do with rate. And that's what they were trying to ask. And so, Catherine, that's how this ties back, is that it doesn't matter how long it takes. They'll come to the same equilibrium. Correct. You guys good? Okay. So, guys, now we're ready to move into some stuff that's going to feel like review. And I'm happy to spend as much time on this as you want. If you understood this, chances are good the amount of time that we need to spend on this is none. Okay, so let's talk. So, guys, the next thing we need to work through is this idea of the mathematical representation of equilibrium. And guys, when we study equilibrium mathematically, we write these KC expressions. I really don't think you need to write this down. But fundamentally it goes W moles of A plus X moles of B in equilibrium with Y moles of C and Z moles of D. Remember, products go on the top, reactants go on the bottom. The brackets mean concentration, molarity. Then we've got our reactants. And then, guys, here the coefficients are the exponents. Don't confuse this with rate laws where the exponents, the reaction orders, here they are the exponents. You okay? Go ahead. Yeah, it's a great question. Frankly, Alyssa, what I'm doing right now is sort of counting the cost. We could spend 10 minutes and talk about why. And to be honest with you, I'm really tempted to do it because it's fascinating. But I don't know that it buys us much down the road. So I'm trying to think if there's a way that I can say it like succinctly, because it has to do with mechanisms. Let me try this. And frankly, if you hate it, this is the best I can do without spending the 10 or 15 minutes that it would take. But what about this? So Alyssa's question is, why are the coefficients the exponents in these things, which are called equilibrium expressions, but why are the coefficients not the exponents in rate laws? The answer might be best understood by flipping the questions around. So let me turn it to you. Why are the coefficients in a balanced equation not the exponents in a rate law? Why doesn't that work?
Because the reaction that goes.
Because the mechanism could be doing something crazy. Does that make, let's pause there. This is actually, we're going to do this. It'll take 3 minutes instead of 10. So let's talk about it. So guys, why is it, make sure you're clear, why is it that the coefficients in the balanced equation, why is it they are not the exponents, the reaction orders in a rate law? The mechanism could be doing something completely weird, right? If we just took the balanced equation and made it into the rate law, it could be that some of those reactants don't even change the rate of the reaction. So it's not that simple. We can't just take the coefficients and make them exponents because the rate law is dependent upon the mechanism, and the mechanism is not represented necessarily in the balanced equation. Does that make sense? Is that okay? So now let's ask this. Why are the coefficients the exponents in the equilibrium expression? And the answer is because it doesn't matter how it gets there. All this thing is representing is products divided by reactants. It doesn't matter how it gets there. It doesn't matter, Brandon, importantly, how fast it gets there. It just matters where it goes. And because it doesn't matter how it gets there, this then does become an accurate representation of the reality, because all we need to know is how much product, how much reactant. And because this is an appropriate representation for an equilibrium expression, we can use the coefficients as exponents. Okay? That's not a bad answer. Understand that if you still want to ask the question, but why, then we would have to get into molecularity, elementary steps in the fundamentals of mechanisms. We don't need to do that, but that's the big picture answer. Go ahead. Good night. Yes. And what if we said this? It depends on the stoichiometry and not the collisions that take place in the mechanism. That's exactly right. So the equilibrium is only determined, the conditions at equilibrium are only determined by the stoichiometry. A rate law, which describes the rate of the reaction, is dependent upon collisions and mechanisms, and that's a whole different story. Yeah, Kami, that was a great summary. Y'all good? We good? Okay. So, guys, let's just say this. And again, you know, Catherine was wrestling with the terminology. Guys, this thing is called an equilibrium constant. This Kc, no. Let's just be really, you guys are picking this apart. So, well, no, I'm going to leave it as it stands given the next bullet. So guys, this is what is called Kc, well, K is the equilibrium constant. The fact that we're adding C to it means that it's an equilibrium constant relative to concentration. Guys, this is no, we're going to deal with pressure in this unit. What you're going to see is when we get into chapter 16, we're going to be Ka, Kb, Kw, Ksp, Keq, Q, which is K not at equilibrium. You're going to love it. But interestingly, Kami, I didn't even pick up on this. Look at the next bullet. It's exactly what you said. That K is only dependent upon the stoichiometry. It has nothing to do with the reaction mechanisms. Therefore, the coefficients are the exponents. It's funny though, Alyssa, without you having asked that question, I would have never thought that this simple sentence actually describes why we can use the exponents in one case and not the other. That's interesting. Go ahead, Brent.
I'm kind of backwards, but the KF over KR, that one.
Uh-huh. The little k.
Yeah, I think after saying the products of reactants.
Uh-huh.
There's a hard time picturing.
So let's go back to our tubes. Okay? Big tube, little tube, right? Cylinders. When we did the flippy thing, it ended up 70-30. Why did it end up 70-30? No. Pretend this has nothing to do with chemistry and it's just the fun of moving water around. One tube is bigger than the other, right? So we have a relationship. When we reach equilibrium, we knew that it was 70-30. What caused it to be 70-30? The diameter of the tubes. So now we have two ratios. We have a 70-30 ratio, which is representative of the concentration ratio. We also have the diameter ratios of those two tubes. And correctly, somebody suggested that the bigger tube is 7/3 bigger than the smaller tube. Their radii are actually 7-3. And so the idea is this 70-30 concentration ratio is a function of the diameter ratio of the tubes. What do the tubes represent? The little k values. So if we could measure the diameters of those little tubes, it would be 7 divided by 3, forward divided by reversed, right? If we could measure the volumes, it's also 7 divided by 3. And that's what she's saying, is that the rate constant ratios cause the Kc ratio, the equilibrium ratio, and those ratios are equivalent and they're both equal to Kc because one causes the other. You guys good? You're good? All right. So now, guys, we're going to move into some new stuff, the important stuff. So here we go. Bringing this into another context, guys, we need now to talk about gas equilibria. So I would encourage you to be, you know what, guys? Would you just trust me and not write any of this down? Promise?
Yes.
Okay, so guys, here's the deal. When we talk about Kc values, we're talking about concentrations at equilibrium, right? Yeah? Okay. Well, it turns out that we can also study gas phase reactions. Can you imagine the Haber process? Nitrogen is a gas. Hydrogen is a gas. NH3, interestingly, is also a gas until we dissolve it in water. So guys, all of these things are gases. So if we were to take a steel vessel and we were to charge it with nitrogen and hydrogen and allow it to form ammonia and come to equilibrium, it would not be best to study that given concentrations because these are gases. Technically, they don't have concentrations. But what do they have? Pressures. And so think about this, guys. You already know this, right? This is reactants. What happens to the concentration? What happens to the concentration of reactants as the reaction goes on? Goes down, right? Well, guess what? If those reactants are gases, what happens to the pressure of those gases as the reaction goes on? Also goes down. Doesn't that make sense? That they're being consumed. And as they're consumed, there are fewer of them, and their partial pressures go down. So it's exactly the same logic as concentration ratios. It's just with gases, instead of studying concentrations, we study partial pressures. Hold on. So, guys, it rolls out like this. We call these things Kp values. Notice the difference. This is a P instead of a C. And instead of this being brackets, which means molarity, it's now parentheses, which means here comes a number. And that number is the partial pressure of all the gases. So it's still C and D products, it's still A and B on the bottom, reactants. The coefficients are still exponents. It's just now, instead of tracking molarity for solution-based chemistry, we are now tracking pressures for gas-based chemistry. No need to take notes, right? Go ahead.
Why don't we analyze the concentration?
And this is an interesting point because, guys, did you understand what we just talked about? If it's a solution-based reaction, we do concentration. If it's a gas-based reaction, we do pressure. Do you understand that? Here's what you're going to see in the book. You're not going to like this. But let's answer your question first. So why with gas phase reactions do we study pressure instead of concentration? Well, concentration is molarity, right? What are the units for molarity? Moles of solute divided by liters of solution. But gas phase reactions are not dissolved in water. You don't have a solution. Do you see what I'm saying? Does that make sense, y'all? Because this is what you're going to see in the book that you're not going to like. What they're going to do is they're going to do something like this. They're going to say, hey, you have a 1 liter vessel, and you put 0.1 moles of H2 and 0.1 moles of N2 inside that vessel, and you let it come to equilibrium. Gas phase reaction, right? But here's what they're going to do. They're going to write a Kc expression for this. Kc. Here's the logic behind it. And now you're going, wait, no. This is gas phase. This isn't concentration, this is pressure. Here's what they do. Guys, we understand that concentration, molarity, is equal to moles of solute divided by liters of solution, right? You're not going to like this. Here's what they do. They make up a brand new unit of concentration using the fundamentals of molarity, but it's moles of gas divided by liters of vessel. The volume. And it actually works. The reason it works is everything about Dalton's law of partial pressures, and we don't need to get into it. But guys, when you get into the homework, what you're going to find out is sometimes when we study gas phase reactions, we'll do it using pressures. But we can also do a concentration study of gas phase reactions. But when we do, the molarity is the moles of each individual gas divided by the volume of the container. Now here's the thing that's interesting. When you do that, say that you were to take this reaction and you were to study this using pressures, and then you were to study it using these made-up concentration units. Guys, here's the thing that's interesting. The values are generally different. You may see that on the test. So, if you're studying a gas phase reaction by looking at partial pressures, and then if you go back and study the same gas phase equilibrium using these made-up concentration units, the values will actually be different, typically. It used to be that on the AP equation sheet, there's actually an equation that relates one to the other, but they took it away, so we don't need to talk about it. So you guys good on this? Well, no. So the thing that we're missed, so what's going on here is so that's the balanced equation, right? So if we were to write the Kc, it would be the molarity of NH3 squared, the molarity of H2 cubed, and the molarity of N2. If we were to make this into a Kp, these would then become the pressures of, that's such a mess, but you understand what I'm saying. Yeah, and that you got to have products to have an equilibrium. Yeah.
So on like the chapter summary, just like the equation Kc times R times T.
Raised to the number of moles. That's the equation that they took away from us. Great. You can do it in homework. You won't see it on the test. You'll figure it out. Yeah. You guys good? Alrighty, so let's get rid of that. And now, guys, we're ready to get into what I find to be the most interesting portion of this material. So let's do this. We're going to not wrap up the day. We're not close. But the conclusion of the day is all about the so whats. Okay, so we understand Kcs. We understand their product divided by reactant ratios. But what do we do with these things? Well, guys, interestingly, the answer to that question, what do we do with these things, is everything we're going to do for the rest of the year. Literally, the remainder of this year is going to be based on K values. That's it. This is what we're doing until the end of March. Then it's spring break. Then it's get ready for the AP test. And not a day, well, 2 days will go by when we do not talk about K values. These are the big deal. So, first of all, guys, let's talk about the information that is contained in K values. Okay, you just calculated a K value. So what? So guys, what information is contained in these reactions? Well, guys, the first thing we understand is the magnitude of Kc tells us the direction that a reaction will, well, let's say it differently. It tells us the direction the reaction favors at equilibrium. So guys, what does it mean if Kc is big? Huge. And when we say huge, we are talking on the order of millions to trillions. So you calculate Kc, and the value for Kc is 1.5 times 10 to the 6th. What does that tell you? What does it tell you? Hugely favored. And do you guys understand that? Products is on top, right? So guys, this tells us, and that is I know I never felt like I'd have to prompt you to take notes, but guys, I would write this down because this is the way to say it. The reaction favors products. But guys, there's another interesting way to say this. Try this one on for size. The equilibrium lies to the right. Do those? Yeah, right. So now we're a Le Chatelier's principle, right? But guys, do you see how those two things are synonymous? Going to the right, the equilibrium lies to the right. The equilibrium favors products. Products are on the right. We're saying the same thing. We okay with that? Well,
Greater than 1.
right, and that's where we've got to be careful, because what's the other side of this conversation? So if it's big, it's small, but what does small mean? Right, but what does small mean numerically? Right, but yeah. But guys, here's the thing you got to be careful of. Don't confuse less than 1 with less than 0. Right? Kc cannot be negative. To generate a negative Kc value, you'd have to have a negative concentration, and that's obviously, or a negative pressure. Those are impossible. So guys, when we talk about small, we mean much less than 1. And guys, we are going to be dealing with Kc values, especially in chapter 17. We're going to be dealing with Kc values on the order of like 10 to the negative 11th. Really small numbers. So what is big and what is small? You're going to find out, and you don't need to know this now, but I'll just plant the seed with you. When we get into chapter 16 and then 17, where we start talking about acid and base equilibria, the cutoff between big and small is 10 to the negative 4th. Anything bigger than 10 to the negative 4th, we're going to consider to be big. By the way, relative to acids, what does it mean to be big? Strong. We'll talk more later. But, so guys, the cutoff is about 10 to the negative 4th. If you're dealing with things on the order of 10 to the negative 4th, you got to tread lightly. Anything smaller than 10 to the negative 4th is small. Anything bigger than 10 to the negative 4th we call big. But regardless of that, for right now, we can just call it 1. So big numbers are bigger than 1, small numbers are smaller than 1, but not negative. But then, guys, of course, these things are true, right? If you've got a Kc value less than 1, small, then the denominator is bigger, and that's the reactants. So the reaction favors reactants, or similarly, the equilibrium lies to the left. Is that okay? Is about what you're thinking?
Left and right of what?
The yields arrow. Yeah, so we've got this idea that reactants in equilibrium with products, so this would be left and that would be, yeah. But guys, Isabel's question brings up an interesting point. What if we flip the reaction over? Exactly. Does that make sense? So guys, if we write the Haber process, and I'm going to be, oh gosh, if we write the Haber process, and I'm going to be sloppy about this, if we write the Haber process like this, then these are our products and those are our reactants. But guys, we could easily do this. I'm not balancing it, but you get the idea. Guys, if we flip it over, how does this work? Well, if we know the Kc value for the top reaction, what would the Kc value be for the bottom reaction? Flip it over. 1 over Kc. Or Kc to the negative 1. Ooh, did we learn that this year? Oh, boy. So, guys, it would be the inverse, or 1 over Kc. You guys good? You okay? Yeah, when you flip it over. Okay. So, guys, you're good on these ideas? Okay, so now you're going to learn something about equilibria that is going to change the way you study equilibria for the rest of the year. This is going to become an important guiding principle for you forever. And it goes like this. You're going to want to get this down. Guys, there are 2 different types of equilibria. Just like there's 2 different types of matter, Homo and Heterogeneous, just like there's 2 different types of catalysts, but don't try to make too many connections. Guys, there are also Homo and Heterogeneous equilibria. Let's talk. So a homogeneous, not surprisingly, equilibria is an equilibria where all the reactants or products are in the same phase. An example of that, not surprisingly, would be the Haber process. Nitrogen's a gas, hydrogen's a gas, ammonia's a gas. So, again, not surprisingly, if we've got Homo, we've also got heterogeneous. And again, not surprisingly, a heterogeneous equilibria is where we've got substances in different phases. You good? So guys, you now have quite literally 60 seconds to write the Kc expression for the reaction that takes place in solution between soluble potassium iodide and soluble lead-2 nitrate. Ready, go. Well, maybe I shouldn't have said. There's water around. If these things dissolve in water, represent them as such. If I only remembered the solubility rules. But I'm probably going to have to know them for the AP test, so maybe I should start looking at them again. That's the part you missed because I put up the white screen. There's your balanced equation. I did it in 60 seconds. How about you? You got it? Hold on. Let me lead. You guys good? You okay? We wrote the balanced equation. We wrote the KC expression. Now, guys, it's wrong. And we need to talk about why. Maybe some of you picked up, given the category, the heading in your notes. But, guys, looking at, I don't want to spend the time to draw the picture, so let's just go back to the equation. Let's put subscripts on here. Does potassium iodide dissolve in water? Yeah, it does. All halogens dissolve in water unless they're bonded to silver, lead, 2, and mercury. Do all nitrates dissolve in water? Oh, baby. But what happens when iodide as a halogen bonds to lead 2? It no longer dissolves in water, and it's a solid. That's a solid. It settles to the bottom of the beaker. It's a precipitate. Good. Yeah, it's a precipitate. Guys, we now have a glaring contradiction. Because if we are going to try to solve for Kc, we need values for all of these numbers. We need to know the molarity of potassium iodide, the molarity of lead 2 nitrate, the molarity of potassium nitrate, and the molarity of lead 2 iodide. Do you see the problem? Guys, molarity is moles divided by liters, right? Moles of solute, liters of solution. Here's the problem. This stuff doesn't dissolve in water. If it doesn't dissolve in water, it doesn't have a concentration. And that's different than 0. Guys, a molarity of 0 means a substance that could dissolve in water, but you haven't added it yet, or it hasn't been produced yet. And understand that lead 2 iodide does not have a molarity of 0. It is incapable of having a molarity. That means it does not go in the equilibrium expression. You just get rid of them. The reason is because it's not that they don't have a molarity, it's they can't have a molarity. Now, when you get to college, I'm sure that you'll run into professors that will better explain that. But guys, the functional reason is because it can't have a molarity, which is different than doesn't. University professors would never teach it this way, but functionally for us, it's sufficient. But the thing that you've got to know, guys, and maybe we should say this. Do you see how this fits into our conversation? This is heterogeneous, right? We've got aqueous ions and a solid. They're in different phases. That makes it heterogeneous. And guys, many times you will see this in heterogeneous systems. But it doesn't stop there. Liquids are the same way. So guys, when you are dealing with heterogeneous equilibria, you will always disregard pure solids and pure liquids. And if you don't know what I'm talking about, typically the synthesis of water goes to completion. But if it could reach equilibrium, what would the K expression look like? Well, guys, hydrogen is a gas. Oxygen is a gas. Water is a liquid. So, right, so when we write the KP, KP for this, our product would be, I'm really struggling. Right. when we do this, we would go Kp is equal to water squared hydrogen squared oxygen. But guys, these are gases. Oh gosh, no, sorry, this would be parentheses P, parentheses P, parentheses P. You get the idea. But guys, liquid water does not have a pressure. It's a liquid. So the Kp for this would actually not include this, and it would be 1 over the partial pressures of the reactants. Yeah.
For the past example with like the PBI,
Mm-hmm.
wouldn't it still be able to dissolve that into iodine and like lead? Because it says like once it's dissolved,
Right.
it's no longer affected.
No, good. Do you understand what Matt's saying? Wow, I'm a little embarrassed you guys didn't catch that. But your question is good. Can this still break apart and turn into those? It's an equilibrium. What's the answer? Absolutely. So guys, please hear this carefully. Is the PBI2 important to the reaction? Oh yeah, if it's not there, this can't reach equilibrium. If it's an equilibrium process, it can't go the other way without this. So is this important? Yes. Does it have a concentration? No. And those are different. It is important to the reaction. When we disregard it here, it doesn't mean we get rid of it from the balanced equation. It's got to be there or this doesn't represent the chemistry. That said, it doesn't get represented here because by definition this is a case C and it doesn't have a concentration. Does that make sense? So it's got to be there, it just never is there because it doesn't have a concentration. You good on that? Okay. Guys, we good on this heterogeneous stuff? You okay? All right, so let me do this, let me do this, let me do this, let me do that, drawing dots. And guys, frankly, okay. Guys, we are going to call it quits there. But we're not done. But what we are going to do is there's one more thing. Well, never mind. Let's finish. We'll get done in 5 minutes. But we'll make sure that we answer questions carefully when we do. So guys, last thing we're going to do is we're going to talk about reaction quotients. Scratch it in your note. Right there. Reaction quotients. So guys, do this with me. Reactants, products. Let's write the KC. Thank you. Good so far? You're nervous. You're going, he's going to trick us eventually. I am. I know. Education through deception. There's actually, do you know this, an ed psych term for education through deception? It's called cognitive dissonance. Yes, my master's degree is in ed psych. So, guys, when we have a reaction, and this is important, it's subtle, but it's important. When we have a reaction, when we write a KC expression, what values go in the brackets? And I'm not trying to trick you. This is tricky in a different way. So this is tricky in an interesting way. So guys, what values go in the brackets? Molarities, right? But this is important. Molarities at what conditions? Equilibrium. Do you understand that? Guys, if we go back to our graph and we've got reactants, that was surprisingly good for a left-handed guy. You know what we're talking about, right? So we've got time, we've got concentration, and guys, we understand that initially we've got a lot of reactant, we've got no product. We've seen this before, right? So the question is, what values do we plug into these brackets? And the answer is these values, right? The numbers that necessarily go in the brackets are the concentrations at equilibrium. Does that make sense? Now, guys, here's the question. What would happen if we plugged in these? Oh, I wanted to switch colors. Is that okay? I'd like to make it blue, just because blue feels better. So, guys, what would happen if I plugged in these? I've never taught this way. This is brilliant. What would happen if we plugged in these values? Well, guys, let's do it. Let's label our things. Which one's our product, the bottom or the top one? This is our reactant, right? It's going away. This is our product. So what if we plugged in the values at these conditions? Well, what would the product number be? Would it be higher or lower than it would be at equilibrium? Lower, right? This would be too small. What would the reactant value be relative to what we would have plugged in at equilibrium? Too big, right? This would be too big. So relative to Kc, right? Kc is at equilibrium. Relative to Kc, what would the result of this calculation be? Would it be bigger or smaller than Kc? Way smaller, right? We've got too small a numerator, too big of a denominator. That value would be too small. Does that make sense? So this would be too small. Guys, what we just did is called a reaction quotient calculation. Write this down with me. This is called Q. Q is the concentration of products divided by the concentration of reactants. Sounds familiar, right? Q is Kc. These are the same. But what's the difference? Kc is at equilibrium. Q is in any set of conditions. Let that soak in. Kc, by definition, is based upon the equilibrium concentrations. Q is Kc solved at any set of concentrations. Does that make sense? So just a second. Let me roll with this for just a second. So guys, what value does Q have for us? Well, check this out. Go back to this calculation that we did right here. So we took those numbers from being before equilibrium. And before equilibrium, we've got too much reactant, and we don't have enough product, right? So we did that blue calculation before equilibrium. Because we did it before equilibrium, we've got too much reactant and not enough product. What did that do to the value of Q? Made it too small, right? So here's what we can then say. If Q is less than Kc, write this down with me. If Q is less than Kc, what does that mean? Well, guys, if Q is less than Kc, it means this will be 2 minutes. Right. Yes. If Q is less than Kc, then we don't have enough product, and we've got too much reactant. So what is that reaction going to do to get to Kc? It's going to make more product. Does that make sense? So what if the opposite were true? What if Q were bigger than Kc? Well, if Q was bigger than Kc, now we've got too much product. And what's the reaction going to do to get to Kc? Get rid of product and make more reactant. That's the forward and reverse stuff. And guys, you're going to see that we're going to learn about this now. And then in chapter 20, when we talk about electrochemistry and batteries, we're going to use this concept to figure out how batteries function as they move electrons between their poles. So right now you just need to understand this. So let's summarize. So guys, here's what we now know. We know that Q is equal to products divided by reactants. This is our big summary if you want to write it down. Q is products divided by reactants. Hi.
Hi, do you want us to come take pictures today?
Yeah, you're welcome to, but grab a seat right now. I got 2 more minutes.
We're just going to get cameras.
Come on back.
Thank you.
All right. So, guys, what if Q is bigger than KC? Here's a great way to think about it. If Q is bigger than KC, which is too big? The products in the numerator or the reactants in the denominator? Products in the numerator, right? If Q is too big, that's too big. So what is the reaction going to do? Well, if reactants turn into products, and if the products are too big, the reaction's going to go that way. It's going to get rid of the extra product, and it's going to turn it into reactant. Now, guys, what if Q is less than KC? Guys, if Q is less than KC, now which number's too big? If Q is too small, which number's too big? Reactants. Now we've got too much reactant, so now the reaction's going to go that way to get rid of reactant to turn it into product. So guys, the value of Q tells us which direction the reaction will proceed towards equilibrium. Not bad? Okay, so guys, we're done. You now have your homework. Which is here. I think you've already seen it. We will grade this on Monday. And then, guys, we're going to get... Oh, wait, guys, remember Monday?